Hi grade 11s. We just want to continue with the term 2 work, and our first topic for term 2 is trigonometry, or actually trig identities. This notes was sent to you earlier. I just want to do an explanation, and thereafter I'm going to get a video ready for you with the solution. Now, trig identities is a mathematical statement that is always true for all values of angles with exception. So note that tan of theta is undefined for theta equal to plus minus 90 or plus minus 270, and all these values and the multiples of these values. So there are some restrictions in which the identities may not work. Identities are used in order to simplify trigonometric expression, in other words, proving identities. In grade 11, there are two fundamental identities which you have to learn for examination. That is the proofs of these ones. They are fundamental. The first one is sine squared plus cos squared equals 1. And the second one is very useful, that tan of theta can be expressed as sine theta over cos theta. The identities have to be used in most cases to simplify expressions or to prove the left hand side of the identity is equal to the right hand side, or vice versa. More clarification of this will follow shortly. Tips when solving problems using identities. Firstly, write expression in terms of sine and cos only, by using tan theta is equal to sine theta over cos theta. Very, very important. Another important useful fact is that 1 over tan is actually cos theta over sine theta. And this is the explanation. 1 divided by tan theta is equal to 1 over 1 times sine theta over cos theta. That's the tan. And because we have division, we change it to multiplication, and therefore it's going to be 1 over 1 times cos theta over sine theta, and therefore it's cos over sine. Some useful information that you could use in your problem solving. When dealing with fractions, and most cases right up to grade 12s, you will be dealing with fractions. So when adding or subtracting, the LCD is important. How to find the LCD? We will do this just now when we do some examples. Factorizing expression where possible is also important. Please make a note of that. And when we do the 3 or 4 examples in these notes, then you will see the importance of all these points. Then you have the first identity called the quotient identities, obviously because of the fraction. We want to now prove this identity from fundamentals. This is examinable. Learn for exams. Can come out between 4 to 5 marks. So once again, it is the left hand side, which is, or in this case it's the right hand side, which is equal to sine theta over cos theta. We want this to be the same as tan theta. So let us go. We take a diagram. We take any angle. It could be an acute angle or it could be an obtuse angle, and it is created by a point R, which is x and y. So therefore that's R, that's y, that's x. So we can get your sine theta is y over r and cos theta is x over r. Exactly what we have here. Long division sign so that you don't get confused. Then second fraction, change that division sign to multiplication. Invert, and you notice the r's will cancel, leaving y over x, which is the right hand side, which is tan theta. Okay, it should be other way about, but this is tan theta, which is equal to the right hand side. Good little small proof. This is the only time you would use x, y, and r. That's for the two fundamental identities. Let's go to the second fundamental identity. We want to prove that sine squared theta plus cos squared theta is equal to 1. Let's refer to the diagram, same diagram as the previous proof. Let's take the left hand side. The left hand side is sine theta over sine theta plus cos theta, which is equal to y squared over r squared. Just to get some clarification, sine theta is the same as sine theta all squared, which is the same as y over r all squared, and therefore that's y squared over r squared. This is important to know, especially squaring of trig identities, or trig ratios actually. Now once again, using the knowledge, you have a fraction added to another fraction, LCD. The LCD of r squared and r squared is r squared. Therefore r squared goes into r squared 1 times the top will be cos y squared, and r squared goes into r squared 1 times the top, which is x squared. They just made it in this order so that we understand the theorem of Pythagoras, that x squared plus y squared is equal to r, using that from that diagram. R squared over r squared is 1, therefore it is the right hand side. We prove the identity using x, y, and r. You'll only use x, y, and r, and this diagram proving the two identities, sine squared theta plus cos squared theta equals 1, and the other one, tan theta is equal to sine over cos. That's the only time that you would use x, y, and r. Now let's examine our first example. So this is a typical type of exam question. In the June exam, maybe in the September, I'm not sure, but in the end of the year, you're going to get one identity to prove between 5 to 6 marks. So they want us to prove that 1 over cos squared theta minus 1 is equal to tan squared theta. Once again, you have two terms, actually two fractions, because this is actually 1 over cos squared theta minus 1 over 1. It's nice to write it down so it helps you in the multiplication of the LCDs. Alright, so let's go through it. So we work with the left hand side, and that's the left hand side, and now this is the explanation I'm trying to give you. Why do we have this situation? Well, the LCD of cos squared theta and 1 is cos squared theta. 1 goes into cos squared theta 1 times the top is 1. 1 over 1, 1 goes into cos squared theta, cos squared times the top. That's the explanation here. When you multiply this out, then you're going to get 1 minus cos squared theta. And something very, very important to note, that if sine squared theta plus cos squared theta is equal to 1, then 1 minus cos squared theta is sine squared theta. In other words, taking this the other side. Very, very important. Right up to metric, you would use this situation. So we have a situation where now this is actually sine squared theta in the numerator over cos squared theta in the denominator, which is tan squared theta, which is the right hand side, thereby proving our first trig identity. Not so bad, but lots of things to remember. LCD, using your square identities, using the byproduct of your square identities. Let's examine another example. Right, a little bit challenging, a little bit confusing, but we're going to do it step by step. So we want to prove that 1 minus sine beta into 1 plus sine beta over cos squared beta is equal to 1. Now this here is very, very interesting. Let us examine something here. Sine squared theta plus cos squared theta is equal to 1 also implies that cos squared theta is equal to 1 minus sine squared theta. Now this is a perfect square, that's a perfect square, so this is 1 minus sine theta into 1 plus sine theta. So this is a useful fact. So in other words, when you see this, one must understand it's the same as 1 minus sine squared beta. And 1 minus sine squared beta is tan squared beta or cos squared beta, and the cos squared will cancel. So we have a game plan now. We know exactly where we're going. So let's take the left hand side. Generally we use the left hand side or the more complicated side. If you take the right hand side, you can do nothing with 1. So we just explain this part here, and that's how they got it. They said multiplying the two brackets. Well, you don't need to multiply because you know it's a difference of 2 squares. So it's 1 minus sine squared beta over cos squared beta. And this is equal to cos squared beta because we explained this to you here. And they did it here as well. So you got cos squared beta over cos squared beta, and therefore equals to 1. Looks ugly, but the more you practice, the more you will learn. This worksheet, there are 10 examples, 4 of which are examples and 6 you must do as homework. But if you haven't done your homework, don't look at the correction video. Try to attempt it, then look at it. Otherwise, you're not going to learn anything. Let's look at example number 4. Example number 4 is this complicated looking one here. Clearly, one can start with the right hand side, and the right hand side would simplify to sine squared alpha over cos squared alpha. But look at the left hand side. There's something in the numerator I can do. I can factorize. This here reminds me of cos squared alpha. If it's cos squared alpha, then I can remove cos squared alpha here and cos squared alpha here and do some factorizing, and that's an idea that I have. So let's look at the left hand side. Okay, write down the left hand side, and then we have this. They're saying to us that 1 minus cos squared alpha is equal to 1 minus sine squared alpha. This part here, this is the explanation they make step by step. No need to rush. Look at the next step. They factorize the top and they factorize the bottom. So they remove a common factor, sine alpha, sine alpha. When you remove sine alpha, you're going to get 1 minus cos alpha on top. And when you remove cos alpha here, then you're going to get 1 minus cos alpha. And clearly, these two will cancel. Therefore, you're going to get sine over cos, and sine over cos is tan, which is the right hand side. So we proved our next identity. Not so bad after all. If you follow the steps and you follow your explanations that I've given you, factorization is important, removing common factors is important, using your square identities, not in sine squared plus cos squared equals 1, but in different formats. Right, so these are your 6 examples that I want you to attempt. The video will be uploaded shortly by tomorrow afternoon. Please do this in your booked 2 and your respective teachers, Mr. Mudali, Mrs. Naidu, and Mr. Kashan, will correct this work for those who have done it, and those who haven't done any work during the lockdown will serve detention and watch these videos and do this work maybe during lunch breaks or early parts of the morning. Thank you. Please make sure that you do this exercise. Try it out before watching the video on the solution. Thank you very much. Have a good day.